Okay, thank you for having me. So yes, I'm going to talk about an unsupervised method for training neural networks. And specifically in a digital holography context. So I'm going to explain a little bit what is digital holography. So this is a hologram. This is something that we record when working with digital holography. These are diffraction patterns caused by blood cells, this exactly, and also calibration beads and the bacteria. But more specifically, it's a coherent wave that comes on the objects and then diffracts towards the sensor and causes these patterns. And the crucial part is that we can apply numerical treatments to reconstruct these objects. And the big difference between digital holography and traditional bright field microscopy is that in bright field microscopy we reconstruct, we obtain the absorption of the object, whereas in digital holography we can also get the phase of the object, which is a really interesting information because it's directly linked to its refraction index. So it's also, that's the main application for that. So let's interest ourselves towards the formation of the images. So formation is made by some linear propagator, something like Rayleigh-Sommerfeld, Fresnel, or Fraunhofer propagator. And then the intensity recording that is done on the sensor is the modulus square of that propagated wave. So one basic reconstruction we can do is backpropagating, so applying the propagator in the reverse direction. And then we get superposition between the objects and a twin image. So this is really a naive way to reconstruct. And what we want to do is use a neural network to remove that twin image and only get the clean objects. One naive way to do that would be to the traditional supervised method, being doing the difference between the ground truth and the network output, which would perhaps be the object plane. But the thing is that we need a really good understanding of what are the ground truth. And of course, we could make a reconstruction through other methods to have that, but that would mean training on estimates of the ground truth, which is not really optimal. So we are exploiting another criterion, is that we actually have the image formation model, which is the propagation and non-modulus square. So we basically have a loop. We go from the holograms, we backpropagate it, we clean it with the network, and then we can repropagate it to get back to the hologram. And therefore, we make the difference between the hologram and the model applied on the output. And this is really helpful because we don't need any ground truth, so this is self-supervised. But the big problem with that is that we are reconstructing complex amplitudes, which is it's twice as much data as what we are comparing it to, which is a hologram, which is real valued. And therefore, it's an approach problem. So what we propose as a solution is to introduce a second propagation distance and a second hologram at that distance, which we're going to compare that distance. And therefore, we alleviate that problem of having more data to reconstruct than what we're comparing it to. So let's see a couple of results here on the left. So a quick disclaimer, all of the results are on simulations and simulations are beat because that's something that we can estimate really easily. On the left, we have the phase of the network inputs with the twin image. And so on the right, we have the network outputs without the twin image. We compare it to a ground truth, we can really see a difference on the projector. So if we zoom in, it's there. We can see the differences on the side of the beats. It's basically in the second and the third oscillations around the beats. So it's really not that much difference. So as a conclusion, I would say that it is a method that works on simulations at least. What we want to expand into is actually experimental data. That's what we are working on. And the really interesting part of it is that we actually can train it only on experiments and not on ground truth that we have to calculate. And the results are pretty good, at least on the simulations, because we have something like 4% relative error on the beats. which is slightly above state of the art, but still pretty close. But it's also quite fast with a third of a second to calculate the language.
Thank you. Are there questions from the audience? I have one. Do you have plans to use real data or to do it on real?
Yes, that's what's currently ongoing. We're trying to see if it actually works with real data. And the thing is that real data is a little bit more complex to simulate, of course. There are a lot of differences between real data. As an example, the illumination, it's not constant, and the simulation is assumed constant, which is not the case. Things like that.
Which kind of data would you use? Always biological stuff?
For now, we are still staying beads because we have beads as data, but yeah, we would expand it to biological stuff like bacteria and things like that. But it's it's still in biology. Yeah.
Other questions from biologists? We should ask a biological question. Don't you think it could be useful to differentiate, like you showed, all red cells, bacteria, just structure here?
You mean making the difference on
Yes.
well, it's not that easy. Well, if you have a trained eye, you can perhaps say that the classifiers it's mixed a lot. You can say that it's bacteria, but you can't really get the value, the quantitativity of the bacteria. You can't really get to you can really get the absorption or the phase of the bacteria just by looking at it. That's why we do it.
So thank you.
I insist on the question, sorry. No, just to say that, for example, when you go for histology, you think of, you have a tissue and someone is investigating whether you have a certain pathogen, or you look at the shape of the cells. So, I mean, so in a way, I guess this is what you were asking, yeah. So, like, when they say distinguish if you're a human or a robot, and you can see all the bicycles, where are the bicycles? So, you think that something like that is possible, or it's beyond what the model can do?
So you mean that the reconstruction on the reconstruction we could basically say what the bacteria is or something like that?
Yeah, something like that.
Yeah, of course we could. Well, but basically everything that is possible in bright field microscopy would be possible in horography. But the thing is that horography would add an additional information, which is the phase, and the phase can actually make perhaps the difference between some bacteria that are really close in shape, things like that.
So it would be another information to help in discriminating. Okay, one cell type from another. Okay, thank you very much. Thanks a lot.